Good morning. This is our third lecture on lecture series on X-ray crystallography and solid-state chemistry. We have been talking about crystal lattice and crystal symmetry. We are continuing this. I said about the crystal lattice, that is a three-dimensional arrangement of lattice point. And the lattice point means that atoms, ions, and molecules of a crystal which are arranged three-dimensionally. And we say unit cell means that the smallest unit of a crystal lattice, which we repeat in three-dimensionally, creates the entire crystal lattice. So here we have a unit cell, and this is an entire crystal. This is an entire crystal. So this is crystal lattice, and this is unit cell. But then, again, we have unit cell of different kind. Unit cell can be broadly divided in primitive unit cell or centered unit cell. And that centered unit cell, again, we can divide in body-centered unit cell, face-centered unit cell, end-centered unit cell, or side-centered unit cell. That has been constructed mathematically in 7 crystal systems. Now we go and look what is primitive and what are non-primitive crystals. Primitive means that in the unit cell, all corners must have a lattice point. That is, lattice point means must have an atom, ions, or molecules. All corner of the unit cell must have one lattice point. Lattice point, I repeat, is either atom or molecule or ion. So again, we will see that a unit cell is shared with 8 unit cells when we arrange it three-dimensionally. So a lattice point in a primitive unit cell is shared by 8 unit cells. Therefore, in a primitive unit cell, we will have only one lattice point. Only one lattice point. 8 into 1 by 8. 8. These are 8 points, corner points, and then these all points will be shared by another 8 unit cells. So that is what we call that a primitive lattice will have only one lattice point. Now the side-centered lattice or non-primitive lattice. This is called also non-primitive lattice. So non-primitive lattice has got 3 possible types: body-centered, face-centered, end-centered. Okay, this is nothing that we have to tell that it is crystallography. It is mathematically derived, possibly in 3-dimensional coordinate systems, that we can have these lattice points, either primitive or non-primitive lattice points. So body-centered lattice means that all the corner points of the unit cell are filled with a lattice point plus another lattice point in the center of the body. That creates the total number of lattice points in body-centered lattice will be 2. And we designate body-centered lattice with the capital letter I. Face-centered lattice, which means that every lattice point at the corner plus center of each face are filled with lattice point. So this is a face-centered lattice. In each center of each face, there are a lattice point. So, mind this every face will be shared by another face of another unit cell of the crystal lattice. So in the face-centered lattice, we have 6 faces. In every faces, we have lattice point, and therefore 3 lattice point here. And for the corner, we have 1 lattice point. So we have 4 lattice point in the face-centered lattice. If we go to the end-centered lattice, it means that we have to have lattice point at the corner plus opposite faces of the unit cell, opposite face of the unit cell. And therefore, if we see that we will have two lattice points in the end-centered lattice. End-centered lattice, again, you say that it can be called a side-centered lattice. So it can be in A phase, B phase, or C phase. Depending on the phase, the lattice points are, we will designate it by A-centered, or B-centered, or C-centered. Okay. So we now know that 7 crystal systems have primitive lattice as well as end-centered lattice. Here we go for how many then we get unique lattices for the 7 crystal systems. German scientist Ludwig Frankenheim in 1845 derived mathematically 15 space lattices. However, after 3 years, in 1948, French physicist Auguste Bravais corrected that derivation and showed that there are only unique 14 lattices in 3-dimensional crystal systems. Though Frankenheim was the pioneer of deriving space lattice, but since it was corrected by Bravais, therefore we call that lattices as Bravais lattice. In cubic crystal system, we can have 3 Bravais lattice. Is body centered, another space centered. Now we might say that why not side centered? Why not side centered? If we take a primitive lattice of cubic center and or any side centered lattice, let's say body centered, and we 3-dimensionally extend it, will that this body centered lattice can also be found in tetragonal system as primitive lattice. Therefore, cubic lattice has got mathematically only possible 3 lattices, that is primitive, body centered, and face centered. Similarly, if we go for tetragonal system, we will see only primitive and 1 body centered lattice. Orthorhombic system has got all 4 types of lattices: primitive, face side centered, body centered, face centered. Rhomboidal crystal system has got only primitive. Hexagonal crystal system has got only primitive, and monoclinic has got only primitive plus side centered, and triclinic has only primitive. So you see that every crystal system has a primitive lattice. Some of them having end-centered lattice or side non-primitive lattice. So in total, we have 14 Bravais lattices. You might ask why we are discussing this. Because if we want to determine 3-dimensional structure of a crystal with experimental technique, we will see that this Bravais lattice plus point group, when we combine, we get a 230 space group. We have millions of crystals, but then if we determine structure, we'll see that crystals must belong to one of the 230 space group. You can see that we are always talking about crystal symmetry. But this is a very essential thing in crystallography. Very, very essential thing in crystallography. But a non-crystallographer can also talk about symmetry. They often say symmetrical object, unsymmetrical object, or sometimes more symmetrical object. So if we take these 2 figures, A and B, a non-crystallographer will immediately say this one has got symmetrical figure, this one is symmetrical figure, and this one is not a symmetrical figure. But this one have more symmetrical elements. So we have to now specify what are symmetry elements and then continue our discussion. Well, you see that this is a Persian tiling design. It has got wonderful symmetry. But when Persian tiling design in 14th century, people probably would not know very much about symmetry. Well, these slides, we see if we place a mirror here, you can see that we see the identical object. So what is this? That if we make a symmetry operation, the object we are seeing, we should create a identical object, exactly identical object by this operation. And the process is called symmetry operation, and the element is called symmetry element. So here we are placing a mirror plane and we get identical object. We can have mirror plane here. We can have mirror plane here as well as here. So these are two mirror plane perpendicular to each other, and we can see that identical objects are formed. Not only mirror plane, but also rotation axis can show us identical objects. There is a two-fold rotation. That means 180 degree. If we rotate it 180 degree, we get that. Here is a three-fold symmetry. 120 degree rotation will gives us through an axis. 120 degree rotation gives us these identical figures. Four-fold rotation symmetry. That is 90 degree rotation through an axis gives us this identical object. So we call that four-fold rotation. Similarly, six-fold rotation is here. That we have 60 degree rotation through an axis, and we get this identical object. So we have rotational axis plus plane, mirror plane we are talking about. Now, you see that we could have one-fold rotation, two-fold rotation, three-fold rotation, four-fold rotation, and six-fold rotational axis. But now, again, question, why not five and seven-fold rotational axis or higher rotational axis? Here is a representation of how unit cells are staggered in a crystal lattice. You see there is no space, dead space in it. We can take one unit cell to another unit cell and extend it three-dimensionally. But if we take a five-fold symmetry, here is a six-fold rotation. If we take a five-fold one, it's a five-fold object. If we stack towards, we will say that we have left out with a dead space or empty space. If we take an eightfold symmetry, you will have an empty space here. In crystal, unit cell do not leave any empty space. Therefore, 5, 7, 8 or higher fold rotational axis, we don't get in classical symmetry. However, very recently, we are seeing crystals having 5-fold, 7-fold, 8-fold, 10-fold symmetry. But these are not classical crystallography. This is pseudo crystal systems. We will not talk it now, we will talk it later. So, symmetry elements I have been talking about. A symmetry element, it's an imaginary line or axis, is a point of reference and about which we do symmetry operation. Let's say, for example, rotation of a molecule through this point of reference is, and we generate the same molecule again. So symmetry elements can describe why you talk about symmetry elements. Symmetry elements can describe the external shape of crystals. So following the types of symmetry elements we observe to study crystal: center of symmetry, plane of symmetry, rotation axis of symmetry, rotation reflection axis of symmetry, rotation inversion axis of symmetry. These are the symmetry elements we encounter when studying crystals in crystallography. So we talked about center of symmetry. You see, here in the unit cell, and the center of symmetry is here of a cubic crystal, center of symmetry. What is plane of symmetry? We take a cube again, and they say that this is a plane of symmetry. And this is a rectangular plane of symmetry. This is a diagonal plane of symmetry. So we talked about center of symmetry, we talked about plane of symmetry, and next, what we call rotation axis of symmetry. We can have an axis there and we rotate in certain angle, and then we get the identical object. We can have an axis here, rotate, and we get identical object. So these are the rotation symmetry of solid. So next we go rotoreflection axis of symmetry. So let's say this is an object. This is our object. We rotate it 180 degree, we get this object here, and then we have a reflection here, and then we get this object here. So this is a rotoreflection axis of symmetry. Here we see that this is let's say this is an object. We can have a rotoreflection in this axis, but we cannot have a rotoreflection in this axis. You see, it is not possible to get rotoreflection. Again, rotation inversion axis of symmetry. What we do now, we rotate first, and then get the object, and then we invert through this point, inversion point, and we get the same object. So we can have roto-inversion axis of symmetry. Well, I said to you, if you remember, that the unit cell parameter are not the only parameter by which we define crystal systems. We must have to have symmetry consideration also. So we have 7 crystal systems. We have unit cell parameters. We discussed about it, but we didn't say about essential symmetry. So cubic, this is the cell parameters, cubic or cubic system. It must have 4 independent 3-fold rotations. If we do not have 4 independent 3-fold rotations, even if we get these cell parameters, okay, but we cannot call it cubic crystal systems. So unit cell parameters plus essential symmetry are the prime indicator to define 7 crystal systems. So tetragonal, we must have 1 4-fold rotation. Otherwise, it would not be tetragonal. Orthorhombic, we must have 3 mutually perpendicular 2-fold rotations, or 3 mutually perpendicular mirror planes. So we will call them orthorhombic. Similarly, for hexagonal, 1 6-fold rotation, as well as these cell parameters. For trigonal or rhombohedral, 1 3-fold rotation, as well as these cell parameters. Monoclinic, 1 2-fold rotation or a mirror plane. And for triclinic, as it has got all parameters are not identical. None of the parameters are identical. So we do not have an essential symmetry for 7 crystal system of triclinic. In this slide, we talked about essential symmetry, and in cubic, we said 4 independent 3-fold rotations. If we go to a previous slide, we'll see that this is a cube. We can have a symmetry operation 3-fold rotation through this axis. We can have a 3-fold rotation through this axis. We can have a 3-fold rotation through this axis. Plus, we can have a 3-fold rotation in any of the A, B, or C axis. And this all include 4 independent 3-fold rotation axes. Similarly, we can show for 1 4-fold rotation, 3 mutually perpendicular or 2-fold rotations or mirror planes and so forth. Now we go to the next slide and we talk about point symmetry and space symmetry. These are very important for crystalline materials. So all crystalline materials possess symmetry. So we have seen now that we have to deal symmetry for crystalline materials to study their structure. So spectroscopists and crystallographers do have different notation for symmetry. Mind it, when spectroscopists are talking about symmetry, they talk symmetry about around a molecule. So take a molecule and then talk symmetry about it. But when crystallographers take symmetry, they have to maintain atomic symmetry of a molecule, atomic symmetry of a molecule. So I mean that in a molecule, there are more than 2 atoms or more than 2 atoms. And for a molecule that is spectroscopy, by spectroscopy, they can also find out symmetry for molecules. So spectroscopists have different designation of symmetry elements. Crystallographers have different designation of symmetry elements. So we are talking only crystallography. So symmetry elements, here are the symmetry elements I talked already. This is point symmetry element. So mirror plane, rotation axis, inversion axis, rotoreflection, and center of symmetry. These are point symmetry elements. We are not talking now space symmetry elements. We talk it later. But then the designation of these symmetry elements for mirror plane is M. For rotation, that is N. So N could be 2, 3, 4, and 6. I discussed it. And then rotoinversion, bar N, that means bar 1, bar 2, etc. And we do not have any rotoreflection for crystallography. We have center of symmetry for crystallography. So this is point group elements. We mentioned here about spectroscopists. They designate it like this. They have mirror plane like this, rotational axis like this, and then they have rotoreflection, which is designated by this. We do not talk this spectroscopic symbolization of symmetry elements. We will be talking only crystallographic symbolization of symmetry elements. So, well, we will be talking about now point group. And point group means that we have to deal with point symmetry elements only. Combination of these point symmetry elements creates 32 unique points group, 32 unique point group for 7 crystals. That has been mathematically derived by German physician Johannes Friedrich Christian Bessel. These 32 point groups of symmetry elements we'll discuss in details in next lecture. Thank you very much for your attention.